Hello and welcome to another creative coding video. Today is actually the last video in the creative coding course, so well done for getting through the whole course. We've actually learned quite a lot and covered quite an impressive amount of ideas, concepts and material. So to finish this course we're going to do something quite unusual and a little bit different, something I've been looking forward to for a while. By the way, don't worry, we won't finish making videos. We will continue making videos on interesting topics or questions that people have come up with, and also worked examples showing how we can use code to create interesting designs. But this video brings to a conclusion the course. So today we're going to stretch our brains a little bit with a bit of a crazy idea. So let's take it slowly. Normally, we write code and that code creates lines, circles, rectangles, colors, and so on. So we write code and that code creates an interesting design. What if we wrote code and that code itself wrote different code and that code created an interesting design? So you can see in this picture here, there's me on the left with a hat on writing code, but then instead of that code drawing shapes and colors, that code when run actually creates different code, and it is that code when run that creates a design. So we're not writing directly instructions for circles and colors. We're actually going to write code which in some sense is going to write its own code. That sounds like a mind-boggling idea. Let's draw a picture just to kind of bring that idea to life. So normally we write instructions and they become a design, perhaps with circles. What we're going to do now is write code which, when run, writes different code, and that code when run draws an interesting design. Now, if we kind of dig into this a little bit and think about what language would this be, this code that we're running to create an image, to make our job easy, it should be a simple language. So we know when we write code here, it is in JavaScript. That's the language we've been using. I might not have mentioned it. It wasn't actually that important. The language we've been learning is JavaScript, and it's been using the P5 library, P5 from processing, which makes it easy to draw shapes and choose colors and so on. In fact, you'll know that we've been using the simple JS extension that I wrote to make that even easier. But imagine us writing code that creates its own JavaScript. That perhaps isn't the easiest thing we could do. I mean, we could try it, but if we start off with the easier task, we will write JavaScript to write some language, and that language then results in drawing patterns. What is this language that we could write that's really simple? Well, some of us, when we were little, played with a robot turtle that drew lines left behind when it moved. And some of you might be familiar with a very simple language called turtle code. It doesn't matter if you're not familiar with it, we can make it up as we go along, we're going to create it. But the idea is really simple. The idea is to imagine a turtle or another animal with a pencil tied to its back, and as it moves it leaves behind a trail, and the turtle follows very simple instructions. This new language that we're going to create is a very simple language. So let's look at an example. So here I've got a simple instruction, just one letter, couldn't get simpler, and it's called F. So it's not fill, it's not circle, it's not a loop, it's just F. And F means forward. Extremely simple. So we can see the turtle, when it's given the instruction F, will move forward. That's really simple, isn't it? We can invent another instruction called R for turning right. So this program, in this very simple turtle language, this program says FRF. Those are the three instructions, and when the turtle is given those instructions, it follows them one after another. F to go forward, R to turn right but not move, and then F again to move forward. And you can see it's left behind this kind of corner shape. A very simple language, isn't it? This is just a slightly more complicated example. FR, FR, FRF. So forward, right, forward, right, forward, right, forward. So it's drawn a square using those instructions. But notice at the end of it, it's not pointing up like it was when it started. Just something to keep in mind. So let's imagine writing some code that has a turtle which can follow these instructions. Let's start simple first. So let's imagine we're writing some code, and imagine we have this turtle already. So I'm logged into Open Processing as usual. I've got my P5, the Simple.js library turned on as usual. Got a simple setup. Now in my draw function, I've just written some instructions to get us started. So I'm choosing a blue color, stroke blue, we know about that. I'm creating a turtle object from a class which I haven't written yet, so we will talk about doing that. But for now, let's imagine we have a turtle. Let me make the text a little bit bigger so we can all see text size. There you go. I hope everyone can see that. So I'm creating my turtle from a turtle class, which we're going to create later. And I'm asking my turtle to move forward, to turn right, and to move forward. Forward, right, forward. We're just doing this to kind of get our hands kind of working with code that can control the turtle. We haven't dived into that turtle language just yet. So in order to make this work, we clearly need a turtle class turtle. If I can remember how to write classes, yep, we did them in a previous video. Now this turtle needs both data and methods. It needs to know where it is, and it needs methods for doing the forward move and the right turn. So let's create a constructor, which you remember from a previous video gets called whenever we first create a object from this class. And we're going to say it's got a location. So So we'll say self.x, let's call it, I don't know, 0. And let's say self.y is 0. And we know we're going to be turning left and right, so we need a sense of direction as well. So which way is it facing? So we can say self.angle, we can just start that at 0. Great. So when this is created, when a myTurtle object is created, that turtle object will have this information inside. It'll have x, y and angle. Now, on its own, this turtle class doesn't do much yet. The first instruction we give it is forward. So let's think about writing a forward method. Actually, let's do the changing direction, because that's actually easier. So let's say it's got a method for turn right. So we say right, and how do we turn the turtle right? What's happening when we say to the turtle, turn right? Well, if you think about it, all that's happening is that its angle is changed so that it's 90 degrees clockwise, turning right. So its angle, self.angle, is updated, and we take 90 from it because adding angles is counterclockwise in the convention, and clockwise is reducing the angle. So we say minus 90 minus equals 90. So when we say turtle turn right, it'll run this method and its angle will reduce by 90 degrees. Great. In fact, while we're here, we can just do a left as well. Turn left. We can say left self.angle plus equals 90, because we're adding 90 degrees to the angle. Okay, so imagine we've got our turtle with a little head, and maybe we can draw a tail. So its angle, let's say it's 0 for now. When we say turn right, we want it to turn in this direction. So its angle is reduced by 90 degrees. When we say turn left, we want it to go in this direction, which means its angle is increased by 90 degrees. Now you can see if the turtle was already pointing in this direction and we said turn left again, another 90 degrees would make it point in this direction, which is what we want. So that simplicity does work. Great, so we've got the turning left and right, but what about the moving forward? Now that's a teeny bit more complicated, so let's look at another picture to help us. Now, in a previous video we talked about trigonometry and working out where we are on a circle as we turn. So this picture looks a little bit complicated, but let's break it down and talk about it. So at the middle we've got our turtle, and it happens to be at turtle x, turtle y here, we call it xy. Now, in order for it to move forward, we need to work out the new x and new y, the new coordinates. Now, if it was only ever moving up, down, left, right, that would be easy. We would just increase and decrease the x and y coordinates. But we've introduced this idea of an angle. And it doesn't have to be a 90 degree turn. We might later choose a 45 degree turn or some other angle. So we need to calculate it using the angle. So we're starting here and ending up here. So we need to work out how far up and how far across it's gone. And we know we can do that using trigonometry, and we've done that a few times before, so if you're unfamiliar, do go back and have a look. So we know from trigonometry that this distance here upwards is the step size, the radius of the circle, times the cosine of the angle that's being turned, that it's at. So let's imagine this is 45 degrees. The cosine of 45 times the step size will give us this distance. And similarly for the horizontal change, it's the same but using sine. You should be familiar with this actually, we've done it a few times before, but if you need a reminder, do go back. So we're saying we want to do a forward method. Let's call it forward. Oops, let me type in the right place. Move forward. Forward is the method. So we need to work out the new location. So we can say new x equals, and is based on the current location, this dot x plus. So we need to be consistent with our angles, whether we add and take away. So if we assume that pointing up is direction 0, angle 0, then angle increases in this direction, which means if we are moving like this, then our x direction reduces. So let's do that. So we want minus. So we want a step size, which we don't know yet. Let's call it step times the sine of this dot angle. That's the current direction it's pointing in. What is step? What's the step size? We don't know. Let's put it in the constructor so it's there. Let's call it step size. Let's say it's 50, just to get started. So it's this dot step, and we do the similar thing for the y direction. Just copying and pasting the code, and this time we use cosine. So that gives me the new location. So it's where it was and where it's moved to. And we just need to draw a line now. We can say draw line. And we can say line from this dot x, where it's currently at, this dot y, to the new x, new y. So we're drawing a line from where it started here to the new x and new y. So we're drawing this line here. So that should leave a trail. But now that we've moved, we need to update the turtle's data to reflect this new position. So we say update position as a comment, and we can say this dot x is new x and this dot y is new y. Can you see what's happening here? We are starting off at xy, self x, self y. We're calculating a new position, new x, new y. We're drawing a line from where we were to where we are now, and then we're updating our turtle to tell it it's now at this new position. Great. This should work, I hope. Will it work? Okay, so let's Let's run the code. Something's gone wrong. Let's have a look at the console, which you can see by clicking on this little button. It's suggesting, well, to be honest, it's not particularly understandable. So let's look at our code again. Where have we made a little mistake? I've spotted it. It's the use of the word self. I'm mixing it up with a different language. It should be the word this, not self. Self is from Python, another language. So it's this.x, this.y. That's what happens sometimes when you learn several languages. They kind of cross over a little bit. Let's fix that. And the same here. This.angle. So we've removed any reference to self. That should work now, hopefully. Oh, still didn't quite. But I can see a teeny weeny dot in the top left. This problem isn't so difficult to solve. What's happened is we've started off at 0 and we have a direction angle 0 which is pointing upwards, and then we've taken a step forward and we've gone off the screen. So let's keep this idea of starting at 0, 0, but whenever we draw something we'll adjust it so that it's kind of 0, 0 is in the center of the canvas. So we've done this before many times. We know that the canvas is 0 to 800 across and 0 to 600 down. We also know that here 0, 0 is in the top left, which is a bit unusual because most people would like it to be in the bottom left. Anyway, we would like 0, 0 to be the middle. So to translate, we just add 400 to the x coordinate and subtract the y coordinate from 300. So x goes across from there and upwards, y goes upwards from there. We've done this many times before. So we say 400 plus this dot x, 300 minus that, 400 plus new xy, 300 minus. That should hopefully fix it. Yes. Is that right? Did I get that right? No, I haven't. I was expecting to go up and across. Yep, I've spotted the error. Making lots of errors today. That should have been a plus. There. It's worth checking to see what you get is actually what you think you should get. So there's a little error in that trigonometric equation. That should have been plus there. Right, let's run that again. Now it works. So we've got a turtle starting and we said F, R, F, forward, right, forward, forward, turn right, forward, and we get this little kind of corner shape. Fantastic. We've made some progress. So let's just pause there and talk about what we've achieved. Small steps, but we've created a turtle object in our code, a class turtle, and we've given it the capability to know where it is, what direction it's pointing, and the ability to move forward, right, forward. Now if we wanted to, we could extend those instructions like this. We can say forward, right, forward, and it should draw more of a shape. And I can say, let's just change that one to left and see what kind of shape pops out. There you go. Forward, right, forward, left, forward. Great. Fantastic. So that's a good basis for what we want to do today. We've created a turtle class and it has the ability to follow instructions in some sense. The next bit is an interesting leap for us. So we'll take it slowly again. Now we don't want to, remember we said we're not wanting to directly code to tell the turtle to move. We want to write our own code which generates this turtle language. So our code will generate this simple turtle language which might have F, R, F, L, those kinds of instructions in, and then that code is run to create a design. How do we do that? Because at the moment we've created the turtle object and we're telling it directly. Well, if we think slowly and carefully and take a step back, the idea of creating your own language does sound daunting, but I promise you that after today's video you should see actually it's not that difficult. So let's take it from first principles. If we have a program in this turtle language, it's got to be stored somewhere, hasn't it? Before we can even hope to run it, it needs to be stored somewhere. Now, where could we store it? Well, it's just a list of instructions. FR, FLR, just a list of instructions. It's a list. So we could have our list, which we've used a few times before, and inside that list are those instructions, FRF for example. So we can have a list called, I don't know, my code, and that list can contain those instructions one after another, and then our code will go through that list and interpret those instructions, interpret the turtle code. So it'll look at, let's say we've got one here. This is our list. F, R, F. That's the list. So the first thing we'll do is visit the first item in the list and say, what is that? Oh, it's an F. So we'll move forward. Next instruction in the list. Right. We'll tell our turtle to turn right. Next instruction in the list. F. Forward. Move the turtle forward. We've reached the end of the program because there's nothing more after that. So this idea of creating a language sounded hard. This idea of having your own turtle code language and interpreting it sounded like something you needed to be, a super whiz to do, has suddenly become doable. We know about lists, we know about working through lists, we know about testing what's in a list, is it an F, is it an R, and then we know how to run those instructions because we've just done it. We've just said turtle.forward, turtle.right. So let's start coding those ideas. So let's at the start of our code create a list. Let's say turtle code program, and it's just a list. Var turtle code equals, and that's an empty list. Let's not make it empty. Let's put something in there. Let's put forward, right, forward, oops, forward, right, forward. In fact, why don't I just extend that a bit by copying and pasting it? So I've got forward, right, forward, right, forward, right. So that's my list, which happens to contain this turtle code. The next thing we want to do, after we've created our turtle, is interpret the code, the turtle code. I'm just writing a comment here to help me think. Interpret the turtle code and run it. So we need to work through each of those instructions, each of those items in the list, and we know that loops can do that. We know we've come across a special kind of for loop, so we can say for var something in or of a list. We've seen that kind of thing before, and what that will do is go through a list and call each item in the list x, and then we can do something with that x. So our list here is actually the turtle code list, and just to be descriptive, instead of calling each item x, let's call it instruction. So what this will do is it'll go through the turtle code list, and for each one it'll call it instruction, and we can then do something with that. And we can then check, is it forward? If instruction equals forward, what do? When we encounter the F instruction, we say to our turtle.forward. Easy peasy, right? Now let's just draw a picture, because I know that there was a bit of coding there and we might have got lost. So let's kind of, we can use this picture. So here's our list called turtle code. Can't read that. We're using a loop to go through it one after another, using that for loop. The variable instruction will first be f, then be r, then be f, and in our loop, as we go through the whole list, we simply check, what is the instruction? If it's an f, then do something. If it's an r, then do something. What are those things? If it's an f, we'll do turtle forward. If it's an r, we'll do turtle right. If it's an L, we'll do turtle left. So let's go and do the same thing for left and right. Let's say right. If instruction equals right, we're going to say turtle dot right. And for the left, the code is almost identical, so we'll copy and paste it. We'll say left. If instruction is L, move it left. Thus this should work now. This should interpret and execute that program. Now let's just pause there, because it's easy to get lost in a page, kind of a screen full of code. We have created a program in turtle code. Here it is. FR. Do I want to put another F on the end? Yeah, I do. Let's add another F. That's our turtle language code, a language we've made ourselves. We are now going through that list, that program effectively, and interpreting it. We are writing our own interpreter. That sounds really massive. When you tell people you created your own language and written your own interpreter, that sounds really impressive, and in some sense it is. But we're just showing you actually how easy it can be. So we're going through that list, which is our program, and for each of those items we're checking, well, what is the instruction? And if it's found to be an F, we're then acting on that and saying turtle forward. If it's an R, turtle right. So we've created our own interpreter, we've created our own language and an ability to execute that program, to run that program. That's pretty cool, actually. This teeny bit of code here, I mean, look, the draw function fits on the screen. Doesn't look like a lot, but yeah, we've done that. We've actually created our own language and an interpreter for it. Let's run it. Okay, a little error. I knew it was too good to be true. Let's fix this little bug. Yeah, it's my turtle, isn't it? My turtle, and my turtle. That should now work. Yep, we've got a square drawn because it's forward, right, forward, right, forward, right, forward. That picture is drawn from this turtle code being interpreted and executed. Pretty amazing, huh? That's not bad. that's I'm still quite impressed by that. I have done it once before, but I'm still impressed by it. Okay, so that's actually, you can take a break here because what we've achieved is quite something. We've created our own language. I mean, we could invent new instructions. We could call something, I don't know, X. We can make a new instruction called X in our language. We can extend our language, and then we can interpret it. We can say, if the instruction is X, do something else. Maybe it'll be a random thing that we do. There's lots of possibilities here. We've got the foundations there. We've created a little language, our own turtle code, and we can extend it if we want to. But I won't do that now. Take a break if you need to. The next bit will be interesting again. So I hope you had a good break. We're back again. Now, what we're going to do is we're not going to rest there. We've done something really cool. We've created our own turtle language. We can extend it if we want to. And we've written an interpreter for it, and it wasn't a lot of code at all. Let's do something really interesting and crazy. Let's imagine that our code is a living thing, our turtle code. In real life, in nature, biology, we have plant cells that split. They divide. And then those split and divide. And as a result of that cell division, things grow, plant leaves grow, branches grow, hair grows, skin grows, and so on. What if we applied that idea to this code? In nature, you have different kinds of cells. We might have an A type of cell, which always becomes an A and a B perhaps. And that A, which we know becomes an A and a B, will become an A and a B, but perhaps a B always becomes an A and an A, perhaps. So the rules here are A type of cell always becomes AB, and a B type of cell always becomes AA. I'm just making this up, but just to illustrate the idea. And if we coloured this, for example, you might have A's that are dark, and you might have B's that are a different colour, like light. You can imagine how you can have some interesting structures emerging, and there are theoretical biologists who think this is how ferns and leaves and trees and things have interesting structures. The part of the mechanism that creates those interesting fractal-like structures often is this kind of simple growth mechanism driven by simple rules. So let's do that to our own code. Crazy idea. So imagine if we had an instruction F, and we wanted to turn it into, so we've got let's say a little program, frf FRF. Now we said we're going to imagine these are our program, our turtle code, is some kind of living thing with these being cells in a way. So let's just say that F, the rule for F, the F cell or the F instruction turns into R, F, LF. So it splits into 4 things. And let's say R just stays R. So that's interesting. That would mean this F grows into, in the next generation of this kind of population, becomes R, F, LF. This R stays as an R, and this R becomes R, F, LF. So from an initial program size of 3, the next generation is 1, 2, 3, 4, 5, 6, 7, 8, 9 instructions in the next generation. So it's grown quite a bit. And if we did it again, that R would stay R, that F would become RF, LF, that L, oh, we haven't got an instruction for L. Let's just say L stays as L. And so on and so on. You can see how you can generate the next generation, as it were, of this program, these living cells, these instructions, from the previous one, and they grow really quickly. It's a picture, a cleaner picture showing that idea. So we start with a program FRF. The rule for growth is F becomes RF, LF. We haven't got one for R or L, which means they stay the same. So the next generation becomes RF, LF, RF, and so on. That next generation, if we ran it, the code RF, LF, R, RF, LF, R should draw this pattern. You can work it out with a pen and paper yourself, but it's different from the very first corner that was drawn with forward, right, forward. So forward, right, forward drew that corner, and the next generation draws this shape. I wonder what the third generation does. Let's try it. Let's work it out. So this one, the R stays R, the F follows the rule and becomes RF, LF, L stays the same, the F follows the rule and becomes RF, LF, 2 R's stay the same, F expanded, L stay the same, F expanded. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Phew. So it's 3, 9, 21, it's grown. That's the idea. We're treating this code instructions as almost like living cells that divide and grow into the next generation. Generation 3 will be bigger, generation 4 will be bigger, but it's interesting to see what is drawn at each generation. Isn't that a crazy idea? Why not do crazy ideas? So how do we code this? So, thinking about how we grow those generations, we start off with a list. Let's say FRF. We don't want to run that code just yet. We want to generate the next generation. So we apply those rules and we have a much bigger program that's come from the first one. So that's generation 1, generation 2. We might choose to go on to generation 3, which will be even bigger. So once we've reached the generation that we want, let's say we want to go on to generation 4, which will be really long, only when we've reached that point do we want to interpret the instructions and draw the lines and shapes that we want. So what this tells us is that all we need to do is we start with our starting program. Instead of interpreting it, we use a loop to repeatedly apply those rules and grow the next generation. So what we're doing is we have a list, we create a new list, and we start populating it as we apply the rules to the first list. And then we do that again for the third generation and so on. Okay, so let's talk as we type because it helps think. So we'll say generate new generations, and we need a loop to do that. So we can say use a loop like a for loop. For var generation equals starting at 1 generation less than or equal to, say let's do 3 to start with, and we're generation plus plus. That's the for loop. So that's going to count from 1 to 3. 1, 2, 3. That's how many generations we want. Not sure if that works in the JavaScript, so we'll say plus equals 1. Now, when we are generating a new generation, as it were, we start with new. We want a new list, a fresh list that we want to create from the old list. So we start with an empty list, new code. So we can say var new code is empty, and then we're going to go through the code, go through our turtle code and apply rules. Let's kind of just leave some space for doing that. And when we've done that, we'll shift, we'll swap them around, we'll point turtle code at the new code. So update turtle code. So we're going to say turtle code, which used to point at this previous code. We're going to say it is the new code. Get my symbols right. So the bit we've not fleshed out yet is applying those rules. How do we do that? We go through the code. And we've done that before, haven't we, when we were interpreting the code. So we can almost copy that, almost instruction by instruction. So for instruction of turtle code, that will go through the instructions. So it will be F first, then R, then F. And instead of executing it, we're just going to build the next generation by applying rules. So we can say for example, growth rule for F, and we can say if instruction equals F. It's very similar to what we were doing before. If it's found an F, we're going to, in the new code, we're going to push onto it what was the rule? It was RF, LF, wasn't it? RF, LF, and those need to be separate items like that. Now you can imagine this can get a bit tedious, writing all those out. There's a shortcut in JavaScript. If I write ... rf lf, that expands that into 4 separate characters. So that's what the ... does. I think 3 dots. There. It's just a shorthand for breaking that up into 4. Just a bit, looks a bit neater. So let's just say what we've done. We're working through the turtle code. When we find an F, the rule is to convert that into RFLF, and that's what's pushed onto the new code list, the next generation. If we don't match anything, if we can say else, so nothing's matched, what do? We don't discard instructions that don't match, we just push them onto the new code, which is pass them through, push instruction. So that's pass through unmatched instructions. So for example, R, there's no rule for R to expand, so when it finds an R, doesn't match F, falls into this else, and we just make it part of the next generation. So by the time it's gone through that code like this for 3 generations, we will have a much bigger program, and then we can create a turtle and execute it. So we're starting with FR. Let's start with something simple. Let's start with FRF. In fact, why don't we use our... Yeah, FRF's fine. Start with something small, because that's what we had when we were looking at our examples here. We were saying start with FRF and then grow from there. This should work. This should work. I hope there's no more bugs. Wow. That's an interesting shape. Let's just check that if we just did the 2nd generation. So we should actually start from generation 0, shouldn't we? And we want to go to generation 1. Now we are starting from the 1st generation and going up to the 2nd. Is that right? No, it's not, is it? We want to only create 1 generation, so we can do that. So it goes once. Yeah, that's right. For loops, we've seen those issues before, just having to think hard about when the loop actually stops. So what I want to do is just create 1 next generation. Starting with the 1st generation, going through the loop and stopping. There you go. And that's actually what we said would happen at the next generation. So that's the generation 2 would draw this kind of upside down T shape. And that's what's happened. Pretty cool, eh? So we've created code, turtle code, that was cool enough. Now we're treating it like a living thing, where each instruction is like a cell that splits and grows. That's a crazy concept, isn't it? Let's carry on and make the next generation, so it's 2 more generations. That was that shape, wasn't it? Now, did we draw a picture of that? Yeah, we did. So, yep, that was generation 1, 2, and the picture is this sort of shape. It's interesting, isn't it? I mean, we're going turn right, turn right, turn right, turn right, forward, left, right. Oh, I can't follow it. But I did do it once, and that's the shape that emerges. And that's what our code's created. Fantastic. I'm going to write a little bit of code here, which is going to tell us the length. Print. Length of the turtle code. Now, in JavaScript, was it turtle code.length? Code.length, I think it is. I'll soon find out if that's right or wrong. So we can print this out to see how long that new code has grown to. So if I run that, I get a little thing in the bottom right telling me something's been printed out. 21. So those are 21 instructions. We counted that, didn't we? We did all that work to there you go, those are 21 instructions. Now, because we're coding, we don't have to stop at 3. Let's say 4. That's 45 instructions. Obviously it's retracing its steps a little bit, but isn't it fascinating how this kind of shape emerges just from growing that simple code according to that rule? It's fascinating. And there are lots of parallels with how nature works here. Let's go 5. 93 instructions. So it's grown to 93 instructions long, this code, and it's drawn this sort of shape. Let's keep going. 6. How big is that now? That's 189 instructions it's grown to. And it's drawing this shape. It might have gone off the screen. So what we can do is make the step size a little bit smaller. Let's say step size, let's call it 20. Let's see if that keeps it on the canvas. Yeah, that's interesting. 189 instructions. There's obviously a lot of retracing the steps going on. It's fascinating the shape that's emerging. Let's carry on for 7 generations. 381 instructions. 8. It's definitely gone off the screen there. Let's go crazy and go 10. 3069 instructions. And let's make the step size smaller so we can see more of it. 5. Wow. So FRF grew to was it 10 generations did we do? 10 generations. After 10 generations of applying that rule, it's grown to a program of 3069 instructions. Just temporarily, I'm going to print that code just so we can see what it is. Where did I do that? There. I'm going to say print. Will it work if I just print turtle code? Not sure. Try it. Oh, it goes on and on. Yeah, so it's quite big, isn't it? There, it's full of FLFL. There it is. You can see it, FLFL, and it goes on and on. 3,000 long. That's fantastic. Now, what you can do, or what you should do, is experiment with your own starting rules. You might not start with FRF. Maybe you'll start with, I don't know, let's say FRR and see what happens. A different starting seed. Wow, look at that. Isn't that interesting? A very curly kind of almost botanical pattern there. And you might change the rule. You might say F doesn't become RFLF. Maybe it becomes RFLFF. Just experiment, see what happens. Wow, that's really kind of grown off the... So you'll find that sometimes things explode a little bit. Maybe I'll make it shorter. RFF. Don't know what that'll do. Different pattern again. I liked having L in. Maybe if I start with F and make things up, just say another F. A different pattern again. So you can experiment there, and I think it's pretty mind-blowing, isn't it? We're starting from some simple starting programs. We're applying a simple rule, and they grow to create interesting shapes. Now we've only got one rule here. We didn't have to. We could say create a rule for R, for example. We could say, I can just copy and paste that code there. We can say else, so else if. So let's create a rule for R. If it's an R, we'll transform it into LF. So we have two rules being applied now. F turns into RFLF and R turns into LF. See what that does? Wow, look at that. That is pretty cool. That is pretty cool. I mean, we can make that stroke a little bit thinner. So we can say stroke weight 1. In fact, we can probably say, use transparency perhaps. We can say 0, red, green, blue, and have a transparency of say 100. So we are not using the first instruction there. That might give us an insight into where that turtle is moving. Yeah, it's interesting there, isn't it? There's paths that are definitely being drawn more than others. So more popular paths, well-trodden paths. That's fascinating. Let's turn that back to 2. Just turn that thickness back to default again. Yeah, look at that. Wow. So there's lots there you can experiment with. You can take a break there. We are going to expand on this a little bit further, so take a break if you need to. I'm going to continue. So, what I'm going to do next is introduce a new instruction to our turtle language. Now have a look at this picture. So we've got code here that looks simple, F, R, F, L, F, but I've got these brackets. I could have used different symbols. I could have called them A and B or E or F or something. I've just used brackets because they're meaningful. You'll see why. What I want this instruction, the left curly bracket, to mean is remember where you were. So let's follow this through. The turtle starts at the bottom. First instruction is F for forward. Forward. Then this left hand square bracket says remember where you were. And then it says turn right and go forward. So we'll end up on the right here. And then that right-handed curly bracket says go back to where you were, the point that you remembered. So it will jump back here. Next instruction, turn left and go forward. So these new instructions are going to say remember where you were, and go back to the last place you remembered. Now you can imagine that as our code grows, let me clear this. So let's say forward is our just instruction. Forward, remember where you were, turn right, forward, remember where you were, forward. So let's imagine going through that. So we're going forward, remember where you were, turn right and go forward, go back to where you were, back to here, and then go forward. How would we implement this in code? Well, we would have to have a place where we stored our position. So when we encounter this instruction, we'd have to say store somewhere your X position, your Y position, and also the direction you were pointing in, so the angle. So imagine running this code again. F for forward, remember where you were, which means we put aside a copy of X, Y and the angle. Then we turn right and go forward. And then when we encounter this instruction, we say, aha, go back to where you were. So we look back at this memory where we stored our previous position, and we say our turtle's X, Y and angle is pulled back from what we stored, and then we carry on as normal. But you can imagine that as our code grows, because we're growing it, or we can write directly, we might have situations where we have more than one. So we might say, remember where you were, forward, remember where you were, forward, turn right, go back to where you were, left, forward, go back to where you were, forward. So we don't want to overwrite this the second time we want to remember where we were. So the first one we'd put there, but the next one we encounter to remember where we were, can't overwrite that, so we need to kind of write it somewhere else. And actually the natural way of doing that is just a list. So we have a list and we put 3 numbers on it, X, Y angle, and then when we encounter it again we say X, Y angle. The only way this is going to work is if we actually roll back in order. So we have to have matching brackets. We can't go back to where we were if that isn't stored. So if we had an extra one of these, that would be an error, because we've stored 2, 1, 2, gone back to 1, gone back to the other one, and then where do we go back to for this one? It wasn't stored. So those need to match. That's okay, I think we can cope with that. So let's think about how let's code this. So we go back to our turtle code template, the class. We might call it sort of save state, because that's what we're doing. So we're saying save where we were. So the method might be called save state. And we need to pop our X, Y and angle onto some kind of list. So we'll create a list in our state list. So this dot state is empty to start with. So when we save state, we say this dot state, push onto it this dot x. So we're saving our x, our y, and our angle. Easy peasy. Sounded hard, didn't it? How easy was that? And then we can do another one for returning state, so restoring where we were, go back to previous position. And we can call that restore or return state. Let's call it restore state. Now we need to pick off those in the order we put them on. What I mean is, if we put angle on last, that's the first thing we need to take off. So we need to say this dot angle is this dot state dot pop. What pop does is take the last item off the list and remove it from that list, so the list shrinks a bit. So there you go. That's what we need to do. We need to take the last item that was on the list, and the last item would have been the angle, and we can just do that for the other two. So the Y and then X. Remember, it's going backwards, so we put X, Y and angle on, so we take off angle, Y and X. Last in, first out. First in, last out. And you can see this will work when we save state twice or three times. You know, it'll grow that list, and as long as we have matching restore states, it'll pull them off. So we've done that, and we've added that to our class for the turtle. Can we do that for our let's write some code that will do that. So we just drew a picture, didn't we? We said forward save state. Can I write it in that way that goes like that? So forward save state, we need 3 dots, forward save state, turn right, forward, return to where you are, forward. And we said that would go forward, 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 right, forward, forward. So that would do, just working it out again. Forward, remember where you were, turn right, forward, go back to where you were, and then forward. So that should draw this sort of shape, like that. Let's make our generations just one, so we don't kind of create a new generation. So we're doing F or FF. In our interpreting code, we need to deal with and interpret those new instructions. So we can say save state and restore state, and it's matching those instructions. So if it's, I'm doing a lot of copy and pasting here, and what that should tell us is there's not a lot of new thinking to be done. We've done the hard work already. So all we're doing here is saying there's a new instruction, this one, and what do we do when we find it? We save state. And for restoring, the instruction is the other one. Restore state. That should work. Hopefully there's no bugs. That should draw that shape. Yep, tiny because the step size is still small from before. Let's make that big again. Step size 50. Let's run that. So that's worked. That's gone forward, remembered where we were, turned right and forward, gone back to where we were, and gone forward. Why have we done this? Why have we created this new, this new capability for our turtle code? Well, it's useful. It's a kind of a shorthand. We don't have to retrace the steps. It kind of gives our code a bit more power, as it were. Because you could have come back with more instructions, but it just saves us having to do that. So that means when we when we do grow code, we can have rules for, we can include them in the instructions. So if we say that's the second, let's do the second generation of that. I'm going to remove the rule for R, just to keep things simple. So we're starting with this code, frf, f, but with those save and restore states. I'm going to create one more generation. Let's see what that does. Ah, that's interesting. Let's create a fourth generation. That's interesting. So you can experiment. Maybe if I do 10 generations with small steps, maybe I'll create something interesting there. Oh, that's interesting. Yeah. Maybe if I put another one in there, like that. So my starting program now has more save states. Not too different, was it? Put another instruction in. It's grown in a different way. Maybe if I put L, F instead of RF. It's just experimenting to see what different kinds of patterns emerge. I'm going to grow to even more instructions. Let's say 16. Wow, look at that. And how many instructions is that? That's 294,912. That's almost 300,000. A third of a million instructions. Wow. There's quite a lot going on there. So you can play around there and come up with some interesting designs. Now you might be thinking, the patterns we've drawn so far have been a little bit samey. And it does take some experimentation to find interesting ones. Now I'm going to show one that I did come up with before. So the starting code here is forward, remember where you were, left forward, go back to where you were, forward, remember where you were, right, forward, remember where you were. Let's draw that out. Let's just see what that might look like. So I'm going forward, remembering where I was, turn left forward, go back to where I was, forward, go back to where I was, right forward. And if each of those forwards has a rule, then you can imagine this might grow in some kind of, I don't know where it'll go, but it's starting off pointing in all directions. Let's try the rule I had before for F. And my rule for F, I can use those new instructions, those save and restore states in that rule too. I can say F becomes F save state RF, restore state, F save state, LF restore state. That's what my rule now also contains, because I'm allowed to do that. Let's see what that looks like. Wow, look at that. That was just 5 generations. It's got 3,000 instructions. That's pretty cool. What does that look like with just 2 generations? By the way, if you have huge numbers for generations, your code's going to grow massive, because it grows almost exponentially, and you might crash the browser because it just can't hold all that in memory. Let's say 3. It's kind of growing in a different way, isn't it, to the previous pattern we saw? Yeah, that's rather nice. Let's say Um, yeah. Now, one last thing to experiment with. Just remember the left and right. We turned directly 90 degrees, didn't we? What if we turned 30 degrees instead of 90 degrees? So when we said forward and then left, instead of going that way, we only turned a bit, and then turning right would be just a bit, 30 degrees. What if that creates a different kind of pattern there? Look at that. Wow. Let me have fewer generations there. I was saving that up, I knew that was going to happen. Let's have 4 generations. Wow, look at that. It's like a plant. Let me grow that for let me make the... what can I do to make that look nicer? Let's make it thin again. Stroke weight 1. And yes, I will use the alpha value for transparency, just to show more where the turtle's drawing. What I'll also do is I'll move the starting point down a bit, so I'll say y is minus 200, just to shift it down a bit. There, look at that. That's amazing. So from our little starting code, and we've grown it for, how many generations was it? 4 generations. And we changed the angle from 90 degrees to 30 degrees, and this kind of tree, fern, grassy thing has emerged. Is that amazing? Does that tell us something about how nature works? I think that's fascinating. Look at that. I might change that to a green, red, green. Make it a dark kind of green. It's not dark enough, is it? I'll remove the stroke weight just to make it thick again. Look at that. Let's grow it for a few more generations. Let's grow it for 7 generations. That might grow off the screen. It did. Isn't that amazing? Look at that. Now, I could fiddle with the rules. I can just make FF. Just have a go yourself. Experiment to see what emerges. I might say turn left twice. It becomes more of a clawed shape. I might... Wow, look at that. So there's a huge variety of designs that can come from this. I'm just playing around here, slightly unguided. That twists to the right a bit. If I grew that for more generations, what would that look like? Yeah, so that's a plant style kind of pattern that emerges. You can have, more geometric designs as well that can emerge. So if I simplified it again and said, let's have a starting rule which was just forward, left, left, forward, left, left, forward. So that's forward, left, left. Ooh, that's going to double back on itself, isn't it? The reason I can do that is because I'm going to use an angle of 60 degrees to change, not 30. So 60. So I'm going to say forward, left 60, which is in that direction, left again, and then forward, then left again, forward. So it would be like that, almost. I think that'll draw a triangle, I think. Yeah, let's try it. Try it for one generation. And the update rule, what f grows into, is f, remember where you were, lf, f. Let's try that. It's tiny, isn't it? Let's make it bigger. Step size 50. Let's go back to having blue. So that's the triangle with just the first generation of code, no second generation. That's kind of what we worked out ourselves. Now if I go a next generation, what does that become? Ah, it's created triangle within triangle in a way. Let's go on for another generation. Let's go on for 4. Wow, look at that. Very geometric. And again, this isn't like that fern tree thing that was growing. This is a very kind of strongly geometric pattern, very regular. But within it, there are some interesting features, aren't there? There's lines that aren't drawn in a way. That's fascinating. Let's carry on for, I don't know, 7 generations. Might need to make this step size smaller. Ba-bum-bum. Step size, say 5. Wow, look at that. It's amazing. And we can rotate that, of course. We can say the starting angle is something like, I don't know, 30 degrees or something. So it's the starting position is different. But you can experiment yourselves. I think, the end, I can carry on here endlessly kind of experimenting, but I hope what you've seen is that this idea of taking instructions and growing new generations, following very simple growth rules, creates all kinds of fascinating designs. There might be more that you discover yourself. I'll stop there and just summarize a little bit what we've done. We have achieved quite a lot today. It's quite packed. We've created our own turtle language. We've written an interpreter for it, which is quite an achievement actually. People think it's a really difficult thing to do, to create your own languages and write interpreters. Our own language was simple, so it turned out to be a doable task, not that difficult. We then took a step further and said, why don't we write code which generates new code, and it's that code that draws the picture. So that's fascinating. We've done that. We've used a method similar to what happens to cells in plants and animals for dividing to grow new code. I mean, this one here has got 5,467 instructions. That's amazing, isn't it? I'm going to show you some code that I've done before. So you can see the code here. The structure is more or less the same. It is the same code, just changed a little bit. And what I've done is added a new instruction in here. So we've got the forward, right, left, save state, return state. Here I've got a new instruction called C, which changes the color, changes the hue, and I'm using HSB to do that. So let's look at how that happens. Change hue. Really simple. So change hue is taking the current hue and adding 5 to it, and then making sure that if it goes past 360 it wraps back around again. I'm also taking the opportunity when I change colour to draw a dot. So fill and stroke is set, and I draw a circle and then change the stroke to something else again. So what this means is whenever in our code, turtle code, the instruction C is encountered, the colour is changed, but also an interesting dot is drawn. Let's see. Look at that. So we have here of that kind of fern pattern growing, but we've got an interesting set of kind of dots with interesting colours being drawn. So that shows that we can easily extend our turtle code to do interesting things like change colour, take the opportunity to draw circles. The possibilities really are endless, and you've just seen how super easy it is to do. I'll bring this to a close. We've done a lot, over the course. We've encountered some really advanced topics, but hopefully made them accessible. If you've worked through the course, you can consider yourself fairly competent. Some of the ideas that we've covered are usually taught at quite a high level, so well done. But the most important thing I want to leave you with is to say, have fun, keep experimenting. That's the best way to learn, and keep creating interesting designs. Bye.